Hi everyone, it's Mr. Baker here with another physics video. Today we're going to be looking at half-life. So we're going to be looking at half-life and we're going to be answering this question. How are popcorn and uranium similar? So people tell me I've got a bit of a rock and roll life, and so what I've done recently is I have videoed popcorn popping. Yes, that's how exciting my life is. So here you can see the popcorn popping away, and I've made a little graph of it. So sizzling away, and after a little while you can see some of it starts to pop. And I've kind of tried to graph how many popcorn kernels pop at any one time. And the graph, hopefully you'll believe me, kind of looks like this. So that's what happened when I popped some popcorn earlier. And I ate it. But this was the graph that I drew from it. And really what I've drawn is the number of unpopped popcorn kernels. And I don't know if you know how popcorn actually pops, but inside there's basically water. And as you heat up the water, it turns to steam and the pressure builds up. And then the inside of the popcorn kind of becomes the outside and it goes pop. And then it turns into popped popcorn. But it's completely random and spontaneous event. You don't know when it's going to happen, and you don't know which one of those popcorn kernels is going to pop next. So random is we don't know which one it's going to do, which one is going to pop, and spontaneous it could be any time that one or any of them pop. And this is the kind of shape of the graph that you get if you graph the number of unpopped popcorn kernels against time. So over time you can see there's less and less of them, and we get this kind of shaped graph. And this is a really important shape of a graph, and we'll look at this and explain this shape of graph over the course of this lesson. Okay, so just like popcorn then, radioactive decay is also random and spontaneous. So here we've got a sample of radioactive stuff, and after a certain amount of time some of them will randomly decay and give off radioactivity. But I don't know which one's going to do that, and I don't know when it's going to happen. So it's random because I don't know which one it's going to happen to, which one's going to give off the radioactivity, and it's spontaneous because I don't know when it's going to happen. But what I can tell you is that after a certain amount of time, half of them will have given off some radioactivity. So we may not be able to say which atom will decay or when, but we can say how long it will take for half of them to. And this is what the half-life is. So here's our definition of half-life then. So the half-life of a sample is the time taken for half of the radioisotopes to decay, or for the activity or count rate to half. So if I show you a little example, I've got a load of blue balls and a load of red balls, and the red balls are new atoms that are formed, so new elements that are formed because the radioisotope has given off some radioactivity and changed into something else. So here I start with a sample, and I start with 16 radioisotopes. So these are radioactive isotopes that will give off radioactivity to become more stable. And after a certain amount of time, in fact one half-life, half of them have decayed. So half of them have given off radioactivity, a new element has been formed, and the new elements that have been formed, the new atoms that are formed, are stable, and the 8 that are left are still radioactive. After another half-life, so now we're up to 2 half-lives, another half of them have decayed, so half of 8 is 4, so altogether there's 12. So I'm left now with 4 of my original 16 that haven't decayed, haven't given off radioactivity, and 12 have, and they've turned into something new that is more stable. After another half-life, after 3 half-lives now, another 2 have given off radioactive radiation, and so we're left now with just 2 left, and 14 out of my 16 originally have changed into something now more stable. So after each half-life, half of the radioisotopes turn into something new and are stable and don't give off radioactivity anymore. How do we measure radioactivity then? We've looked at an example of popcorn, and I've shown you a little model. We can't generally detect all of the radioactivity that's coming off something, off a source, because we use a Geiger counter or a Geiger Müller tube to detect the radioactivity that's coming off. So there's a few definitions that you just need to be aware of. So the source emits nuclear radiation in all directions 360 degrees. So the activity is the number of unstable atoms that decay per second in a radioactive source. So this is all of the radioactive isotopes that are giving off radiation. And the unit of the activity is the becquerel, named after Henri Becquerel. And 1 becquerel is 1 decay per second. Now the count rate is the number of counts per second detected by the Geiger counter. So you're obviously pointing this in one angle, in one direction, and you're not going to get all of the 360 degrees, all of that activity, but you are going to get a proportion of it. So the count rate is directly proportional to the activity, but the count rate isn't the same as the activity. It's not going to be as much. And then over time, we have a net decline. So the overall amount that the activity of a source has fallen by in a period of time is called the net decline. Okay, so there are just a few definitions that you need to be aware of when you're looking at half-life and radioactivity. So now I'm going to show you, this is a model. Originally here there were 100 radioactive isotopes, and over time they have given off radiation and they've become a new element, and you can see that we're getting the same kind of graph as we did when we were looking at the popcorn. It's the same kind of thing happening in that it's random and spontaneous. I don't know which of these is going to give off radiation next and become something stable, and I don't know when it's going to happen. But what I do know is that half of them will decay after 1 half-life, then half of the remaining will decay in the same amount of time, half of those remaining ones will decay in that same amount of time, and that will go on. So the half-life will stay constant, and you can see that. So when we went down from 100 to 50, that was over 1 half-life. Then when we went down from 50 to 25, that was the second half-life. And so we get this graph, which is actually an exponential decay. So let's have a look at a radioactive decay graph then. So we're starting off with 100% of the radioisotopes that are radioactive. They can give off radiation, and over time we'll get this exponential decay, we'll get this decay graph, and after 1 half-life I will be left with 50% of my radioisotopes. 50% of them will have given off radioactivity and will now be stable, and 50% of them will still be left. After the same amount of time again, the second half-life, I will go down by another 50%. And you can carry on doing that over and over again until you haven't got any radioactive particles left anymore. Now the one thing we haven't mentioned is anything to do with background radiation. So when I am measuring radioactivity with a Geiger counter, I will also be measuring the background radiation as well as the sample that I'm detecting. So the first thing I need to do is to not go anywhere near my radioactive sample, is just to have my Geiger counter going, see what the background radiation is, and then when I'm doing any subsequent practicals, I can take off my background radiation so that I can draw an accurate graph. So you can see even on this one, this graph doesn't go to 0, and that can be because of the background radiation that is there present when you're doing these experiments. So sometimes you're given some information and you're asked to calculate the activity or the count rate or maybe the unstable nuclei left using the information that you've got. What we can do is we can use an equation to find this out. So the count rate after a number of half-lives, so n number of half-lives, equals the initial count rate or the initial activity or the initial number of unstable nuclei divided by 2 to the power of n. So if we have a look at an example, so we've got some data here from our graph. So the count rate after 1 half-life is going to be our initial count rate. So from this graph, our initial count rate is 600 divided by 2 to the power of 1, because that's from our equation. We're looking at the first half-life, so 1, so 2 to the power of 1, which is 2. So 600 divided by 2 is 300 counts per minute, and you can see that after 1 half-life here, we go down after 45 minutes, which is the half-life here, we go down to 300. So our equation works here. Let's have a look at another example. So let's have a look at after 3 half-lives. So after 1 half-life, it's fairly easy anyway, because you can just look after the graph or whatever, and that you can work that out. But if you've got to work out the count rate after a number of half-lives, then this is where this is really useful. So the count rate after 3 half-lives would be 600 divided by 2 to the power of 3. 2 to the power of 3 is 8, so 600 divided by 8 equals 75 counts per minute. And if you look after 3 half-lives here, so after 45 plus 45 plus 45 there, you go down and you can see that yes, reading from the graph there, the count rate is 75 counts per minute. Of course, you could do it the other way around if you want to find out how old something is. If you know the original count rate, the count rate now, and what the half-life is, you could rearrange the equation to find n, which would be the number of half-lives. You could then multiply this by the half-life and find the age of the substance. And that's exactly what we do with carbon dating. So carbon dating is a use of half-life, and what carbon dating does is it uses the fact that carbon-14 is a radioactive isotope, and that there is a small amount of radioactive carbon-14 in all living organisms because it enters the food chain. So the giraffe eats the tree, the dinosaur eats the giraffe, and then all of those things, including the dinosaur, dies. So the carbon-14 it contained at the time of death decays over a long period of time, and the radioactivity of the material decreases. The approximate time since the organism died can be worked out by measuring the amount of carbon-14 left in its remains compared to the amount in living organisms. So carbon dating works for things that are up to about 50,000 years old. So actually we couldn't actually date a dinosaur or a fossil from that period using carbon dating, but we could date things up to about 50,000 years old. Right, so that's the end of another lesson, and this one has all been about half-life. These are the things you should be able to do. So you should be able to define the terms activity and half-life and find the half-life from a graph. You should be able to analyse a half-life graph and use ratios to describe how much of a sample remains after a number of half-lives. You should be able to describe what carbon dating is, and you should be able to calculate the changes in count rate using an exponential model using that equation. And we asked at the beginning, how are popcorn and uranium similar? So uranium has a half-life of about 4.5 billion years. Popcorn also has a half-life because the popping of the popcorn is similar in that it is a random spontaneous event. A group of objects that could do this random event spontaneously will have a half-life. The half-life can be described as the time it takes for half of these objects to do this random thing. In the case of uranium, that random thing is to radioactively decay and give off nuclear radiation in order to become a more stable element. Okay, so that's been all about half-life. I've been Mr. Baker, this has been another physics video, and I will see you next time. Thanks very much.